Welcome back friends. Today we are going to study about the mechanical vibrations, different kind of mechanical vibrations like free damp vibration and the dampers using for the vibrations and the vibrations like damp vibration, viscous damping, Coulomb damping, right? So first of all, the different kind of mechanical parameters and components are there. All mechanical system contain three basic components. One is the spring, damper, and mass. In mechanical vibratory systems, there are three parts, main parts. First is the spring, second one is the damper, and third one is the mass. Right? When each of these is in turn in exposed to a constant force, they react with constant displacement, a constant velocity, and a constant acceleration respectively. If you apply force to the spring, if you apply the force to the spring, right, then the stiffness energy or elastic energy or strain energy which is stored in this spring is called as the resisting force, while the force, external force which is exerted on the damper, then damping coefficient or damping capacity of the damper is stored as a damping energy in the damper is called as resisting force. And in the acceleration or if you are applying the external force to the mass, then the acceleration which is produced by the mass is a force, right? Now the fundamentals of vibration for the vibration analysis, when you are going to analyze the vibration, then you have to select the vibrator vibration fundamentals. First, the mass is connect with the spring and damper. Then two energy is stored during the external force produced on the mass. First is the elastic energy which is stored by the spring and damping energy which is stored by the damper. Right. This is the free body diagram. Right. This is the vibratory system, and this is the free body diagram of the vibratory system, right? If you are applying an external force or if the external force is produced with the help with due to the mass, right, this external force or this force which is produced on the vibratory system is due to the mass and due to the gravitational force, right? So due to the force, the two kind of resisting force is produced in the system. One is due to the one due to the damper, and second one is due to the spring. So stiffness factor K into x means the displacement done by the spring or the compression occurs during the force produced is x. X dot c x dot, where c is the damping coefficient and x dot is the displacement or velocity which is produced due in the damping, right? Now, so with the help of this free body diagram we can generate the equation of motion like this: m into x double dot, right? X double dot means the acceleration due to the gravitational force. C equivalent into x dot, right? C equivalent, because if there is more than one damper, then you have to find the equivalent damping coefficient for the vibratory system. Same K equivalent means if more than one spring is used in the vibratory system, then you have to find the equivalent stiffness for the vibratory system. Now there are different kind of vibratory systems. One is the single degree of freedom, two degree of freedom, multi degree of freedom, and continuous system, right? What is the degree of freedom is already studied by us or already discussed by us in the last lecture. There are different kind of vibratory vibration. Was the free vibration, force vibration, free damp vibration, free undamp vibration, force damp vibration, and force undamped vibration, or combination of these modes, right? Means free damp vibration and free undamped vibration is a combination of two vibratory system, and also force damp vibration and force undamped vibration is a combination of two vibratory system. Now, mathematical modeling system. So, if there are mass, more than one mass available in the vibratory system. Suppose this is a vibratory system first, right? There are mass of V plus mass of R, right? Means suppose a rider who rides the bike or ride the vehicle, then the equivalent mass is the mass of vehicle plus mass of rider, mass of vehicle plus mass of rider, right? Now there are many dampers, like this is a strut, right? Strut means a jumper, or you can say is a shock absorber. Then the damper CS, right? Damper CS. In the damper or in the shock absorber, there is a spring which is wounded to the periphery of the damper or wounded to the periphery of the strut, right? So the spring co-constant Ks and strut constant means damper coefficient is Cs. So spring stiffness Ks and damping coefficient Cs. So mass of wheel, this is the mass of wheel means rear wheel, and Kt means another stiffness Kt, another spring stiffness. Same thing is here for for the rear wheel and for the another wheel. Now the mass of rider is also containing spring and damping. So the equivalent vibratory system converts to the 2 times stiffness and 2 times damping coefficient and 2 times wheel stiffness. So the mass of vehicle plus mass of rider, 2 stiffness coefficient and 2 damping coefficient, 2 wheel of mass and 2 stiffness, right? So the single degree of freedom system, so free vibrational of particles like simple harmonic motion. If the simple harmonic motion is there, then the motion of equation is mx double dot plus kx equal to constant. Okay, this is for only single degree of freedom system. If a particle is displaced through a distance of xm from its equilibrium position and released with no velocity, the particle will undergo simple harmonic motion, right? General solution is the sum of two particular solutions. So x is equal to c1 sine under root k by m t plus c2 cos under root k by m t. So x is equal to c1 sine omega nt plus c2 cos omega nt. So omega n natural frequency, natural wavelength is equal to what? Under root k by m, right? We have studied earlier in previous lecture that omega n is equal to under root k by m, right? X is a periodical function and omega n is natural circular frequency of the motion, and c1 and c2 are determined by the initial condition. So x is equal to c1 sine omega nt plus c2 cos omega nt, where c2 is x0. So velocity is x dot is equal to c1 omega n cos omega nt minus c2 omega n sine omega nt, where c1 is equal to vo by omega n. Now simple harmonic motion for the first degree or single degree of freedom system is denoted as x is equal to xm sine omega n t by plus phi, and xm is equal to under root vo by omega n square plus x o square is the amplitude of the wavelength, amplitude of the simple harmonic motion, and phi is tan inverse vo by xo into omega n is the phase angle, and time period is tn is equal to 2 pi by omega n, and natural frequency is omega n by 2 pi. The same thing, the velocity time and acceleration time curve can be represented by sine curves of the same period as the displacement time curve but different phase angle, right? So all this solution is for the simple harmonic motion, right, for the first degree of free vibration system. Now we have to study about the transverse vibration and torsional vibration for the generate the equation of motion, right? So this is the transverse vibration, this is the torsional vibration, right? Now the combination, spring combination, if there are one more than one spring is used, if there are more than one spring is used, then what happen? If the spring are used in the parallel, if all springs are used in parallel, then the equivalent stiffness of the spring is the summation of all stiffness. If this stiffness all spring are used in parallel, then the equivalent stiffness which is determined is the summation of all spring stiffness, right? So the equivalent stiffness is determined as summation of ki, where I is equal to 1 to n number of spring is used. If the series combination means all spring is connected or all spring is used as a series combination, then the spring which is used as spring stiffness means equivalent spring stiffness is determined as the K equivalent is equal to 1 upon summation of I is equal to 1 to n 1 by Ki, right? Now viscous damping. What is the viscous damping? When in the damper, the damping is used or damping is created with the help of fluid, right? Or if we are use a damper, a fluid as a damper, right? If we are used a fluid as a damper to absorb the external force energy or absorb the vibration of the system, then the damping is called as the viscous damping, right? In the viscous damping, damping force is proportional to the velocity and damping coefficient c times velocity dx by dt, right? And the viscous, with the help of viscous, the energy dissipate, or you can say the energy absorbed in the fluid. Dashpot can be designed as in a shock absorber or equivalent effect of energy dissipating capacity determined from test to find the value of this coefficient C, right? Means tau is equal to mu dV by dz, and force which is produced is equal to pi dt mu v by delta is equal to C into x dot. So C is the damping coefficient for the viscous damping is pi dt mu divided by delta. Free motion of damped free motion of damped single degree of freedom system, right? This is a single degree of freedom system where one spring is used, one damper is used, and mass is hang with spring and damper. So the equation of motion is mx double dot plus cx dot plus kx is 0 for the viscous damping, and which is if we are divide this equation by m, if we are divide this equation by m, so we can get x double dot plus 2 zeta omega n x dot plus omega n square x is equal to 0, right? First, how omega n square is here? Why? Because omega n is equal to under root k by m, and here if we divide by m, then we can get k by m, right? So k by m is the omega n square, and z with the help of equation of zeta, we can get c by m is equal to 2 zeta omega n. Why? Because zeta is the ratio of damping coefficient to critical damping coefficient. C by co is equal to c by 2 under root km is the viscous critical damping ratio, and with this equation we can get 2 zeta omega n x dot, right? So solution of the equation of motion, x t, we can get the x with respect to time equal to a e alpha 1 t plus b e alpha 2 t, where a and b are two constant depending on initial conditions. Possibilities depending on the value of zeta to find the alpha 1 and alpha 2. If we want to find the value of zeta, then we have to find the value of alpha 1 and alpha 2 and insert the equation of x with respect to time, right? So there are two possibilities. One is the alpha 1 and alpha 2 is equal to minus zeta plus or minus under root zeta square minus 1 into omega n, right? If we are putting the value of zeta, right, if we are putting the value of zeta is less than 1, then we are getting the value is under them, right? Both root are complex. We cannot find the original value or real value. We can find both value alpha 1 and alpha 2 is complex value. The general solution is x with respect to time is e raised to minus zeta omega n t in bracket a cos under root 1 minus zeta square omega n t plus b sine under root 1 minus zeta square omega n t, right? Time history for the oscillatory motion. If we are considering the free vibration, then the actional force which is produced to the system is for only for the initial motion, right? So when you are applying the initial actional force and then release, then the motion or then the vibration which continuously reduce. So the oscillatory motion or motion which is produced to the system is continuously decrease with respect to time period, but a motion is decreased, or you can say it's a wavelength is decreased, but the time period oscillatory term is going to increase, or wave length is increased, right? Why? So with this diagram we can say that if the vibration, or you can say if the frequency decrease, then wavelength increase. If the wavelength is increase, then frequency should be decrease, right? If the value zeta is greater than 1, then both roots are real, right? And if the both roots are real, then the condition is overdamped condition with oscillatory motion, and the value of x with respect to time is ae minus zeta plus under root zeta square minus 1 into omega nt plus be raised to minus zeta square minus 1 into omega n t, right? Now if we are putting the value of zeta is 1, if we are putting the value of zeta is 1, then what happened? See here, this zeta is equal to 1, then zeta here minus 1 plus under root 1 minus 1 is 0, 1 minus 1 is 0. So what happened? We can get alpha 1 is equal to omega n and alpha 2 is also omega n, right? So double root alpha 1 and alpha 2 is equal to minus omega n. So the equation becomes x with respect to time equal to a plus bt into e raised to minus omega nt, right? Here the condition which is created is called as critical damp condition, right? Now a critical damp system will have the smallest damping required for aperiodic motion, hence the mass returns to the position of rest in the shortest possible time without overshooting, right? Means critical damping means what? You should require minimum damper, or minimum damping is required to balance the vibrating body, right? The property of critical damping is used in many practical example applications. For example, large guns have dashpot with critical damping value so that they return to their original position after recoil in the minimum time without vibrating, right? If the damping provided were more than the critical value, some delay would be caused before next firing, right? Logarithmic decrement we have already studied in last our lectures, so we skip that. Now damp force vibration, right? We had studied the free damp vibration in where in that the force which is produced only initially, after that it will be released from the system, but here the force is continuously applied on the system, so it's called as a force vibration. And also the damper is used, also the damper is used to the system, so it's called as a damp force vibration. For the damp force vibration, the equation of motion is become mx double dot plus cx dot plus kx is equal to pm sine omega f into t, right? So x is equal to x complementary plus x particular, and the magnification factor is required for the damping vibrating system. What is the magnification factor? At zero frequency, the magnification is unity and is independent of the damping, where x is equal to x as t, which itself is the definition of zero frequency deflection. In the force damp vibration, the vibration which is produced in the vibratory system, the deflection of the spring or deflection of the damper is occurs. So we have to magnify the damper, we have to magnify the damper to create or to independent the damper with zero frequency deflection, so it's a magnification factor. At very high frequency the magnification tends to zero or the amplitude of the vibration becomes very small, right? At resonance, resonance means the force frequency, force frequency is equal to the natural frequency, or you can say the frequency which is produced in force vibration is equal to the frequency which is produced in free vibration, then the condition is called as resonance. So the amplitude of vibration becomes the excessive for small damping and decrease with increasing damping. For zero damping at resonance, the amplitude is infinite theoretically, right? This is the vector diagram. We are going to see the forced response, right? In the forced damp vibration, what is the response from the system, right? See, here the spring is connected with mass and damper is also connected with mass. Now I am going to apply, and now I am going to apply the external force and is equal to f0 sine omega t. Then I get the response is ft sine omega t plus phi. Why? Because this is due to the damping coefficient and stiffness coefficient. Output is equal to system function into input, right? Now output x is equal to system properties is the frequency into input is the external force. Input is the external force F, right? So the force response is we have K minus omega square m x is equal to F, right? The basic theory, the force transmitted to the ground is due to the spring and damper. Ft is equal to kx plus cx dot. What we want to know is the ratio is equal to force transmitted divided by excitation force, Ft by F0, right? The force transmitted, force, which force transmitted? Force transmitted to the system. The external force which is applied to the system and the force which is transmitted to the system is called as Ft, and Ft by F0. So from the phase diagram, F0 is the force which is produced to the system or force which is applied to the system. Kx0 is the stiffness factor, so it's the absorb energy by the spring and absorb energy by the damper, right? The force which is applied to the system, and from this force some part of energy is absorbed by this spring and some of the energy which is absorbed by the damper, and then we can find the resultant force which is transmitted to the system. So we can get Ft is equal to x0 under root k square plus c omega square. From now we know that x0 is equal to fo divided by under root k minus m omega square whole square plus c omega square. So we can find the transmissibility of the system, what amount of force can be transmitted or what percentage of force can be transmitted by the system is given by Ft by Fo, and which is equal to under root k square plus c omega square divided by k minus m omega square whole square plus c omega square. And if we are putting, if we put the value of zeta, we can find under root 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square, where r is omega upon omega n and zeta is c upon under root 2 km. Right? How to obtain low transmissibility? Right? Means if the transmissibility is less, then vibration of the system is less. If the force is more transmit or transmissibility of the system is more, then the vibration which is produced of the system is more, right? So for the system or for the safe side, we have to decrease the transmissibility. And how can we obtain the low transmissibility? So t is small, means if omega is number of more than omega n, we want to lower the natural frequency and we want to low stiffness or high mass, right? Now Coulomb friction or Coulomb damping, dry, it's called as a dry friction. How can we find or how can we produce the Coulomb damping, or we can say what is the Coulomb damping? In the vibrating structure, whenever the components slide relative to each other, dry friction damping appears internally, right? As stated, Coulomb damping arises when the body slide on a dry surface, right? Suppose this is the vibratory system. This is the vibratory system. I have applied the external force to the mass. I am going to apply the external force to the mass. Then the mass is sliding, or you can say it's a reciprocate on the surface, right? So the friction is produced between two sliding surface, and this friction is the Coulomb's law. This friction is the Coulomb's law, means the Coulomb's law of dry frictionless states that when two bodies are in contact, the force required to produce the sliding is proportional to the normal force acting in the plane of contact, right? Means the force we have to apply, force we have to apply to move this mass is equal to the friction which is produced between these two surfaces, right? Means if we want to move this mass, then we have to apply as much as force which generate the frictional force between two sliding surfaces. Like suppose we have taken a free body diagram, then this is the mass, then n means the perpendicular force which is oppose the weight, right? Now I have applied the external force on this direction, then the opposite force by the stiffness by the spring is kx, but by the frictional force is mu n, right? It is a mu n. Then the mu n is called as the friction force. Mu n is called as frictional force. So the force required to move this mass is equal to frictional force plus spring force kx, right? The kx is the spring force and mu n is the frictional force. So x dot equal to kx plus mu n is equal to mu w is equal to mu m g, right? So equation of motion is mx double dot plus mu mg sine x dot plus kx equal to 0, right? To find the solution using this procedure, let us assume the initial condition x t equal to 0 is equal to x0 and x dot t equal to 0 is equal to 0. Now we are taking the case 1 when x is positive. and dx by dt is positive, or when x is negative and dx by dt is positive, right? So take the equation mx double dot equal to minus kx minus mu n, or mx double dot plus kx equal to minus mu n, right? So this solution can be determined as xt equal to a1 cos omega nt plus a2 sin omega nt minus mu n by k. How? With respect to previous theory is the viscous damping theory. We can find, or you can say is the from the natural frequency, we can find the equation of xt is equal to a1 cos omega nt plus a2 sin omega nt. But here in the damping, Coulomb damping, the more force which is generated is mu n, right? So minus mu n by k, where omega n is equal to under root k by n, is the frequency of vibration, and a1 and a2 are constant. Case 2, when x is positive and dx by dt is negative, and where when x is negative and dx by dt is negative, then the equation we can find is mx double dot plus kx is equal to mu n, and the equation of motion we can find the x with respect to time equal to a1 cos omega nt plus a4 sin omega nt plus mu n by k. The term mu n by k appearing in equation is constant, representing the virtual displacement of the spring under the force mu n if it were applied as static force, right? If we are applying the external force is a constant, then the force which is produced due to the frictional force is also constant. So the virtual displacement of the spring under the force mu n is also called as a static force. So mu n by k is constant. Why? Because mu n is also constant and k is the stiffness of the spring is also a constant. So we can take mu n by k is also a constant value, right? Note the following characteristics of the system with Coulomb damping. If the Coulomb damping is applied to the vibratory system, the equation of motion is non-linear. The natural frequency of the system is unchanged with the addition of the Coulomb damping, and the motion is periodic with Coulomb damping. The system comes to the rest after some time with Coulomb damping, and the amplitude reduced linearly with Coulomb damping. These five are the characteristic systems with Coulomb damping. Now, the third damping system is the structural damping system, right? But the structural damping system is not in your syllabus, so we are going to skip this portion, right? And going to the next portion is the vibration isolation. If the vibration is produced in the system, then we have to isolate that vibration to prevent the body from any kind of damages or losses. To isolate a device from the source of vibration, we have to reduce the vibration of machine transmission through moving disc, right? We are using the automobile suspension, or we are using the shock absorber which contain the spring and damper to reduce the vibration, right? In the vibratory system we are using the spring and we are going to use the damper. Both are called as vibration isolator. Why? Because both are absorb the external force which is produced to the system and reduce the vibration effect. So this is the vibration isolator, and this process is one of the vibration isolation system, right? The main objective of the vibration isolation system is to isolate the source of vibration from this other system to reduce the vibration transmitted from the machine to base, right? If you are using a washing machine or generator or the other machine, then you are applying the isolator to below part of the system or below part of the washing machine or base of the generator or the other machines to reduce the vibration, right? This is the example. If we are not applying the base isolation, then the whole body is going to vibrate. If we are using the base isolation, then no body is going to, no whole body is going to vibrate, right? The base isolation is used or used for many high rides to prevent from the earthquake, right? The base isolation is used as coil spring isolator with integral viscous damping unit. If we are using the base isolation, then we can prevent the big high rides from the earthquake, right? The force experienced by the instrument or mass is Ft with respect to time is mx double dot with respect to time equal to k xt minus yt plus c x dot t minus y dot t, right? So this is the main part of the vibratory system, and we had studied the single degree of freedom free vibrational system, force vibration system, damp free vibration, damp force vibration, critical damping, over damping, under damping system, and vibrating isolator. And also we had studied the Coulomb damping system and viscous damping system. So that's for today. We had studied next further in our next lecture.